welcome to the second lecture of week 8. So what are we going to do today? Last time I told you that mutation testing means testing for the syntax of a program. Syntax of a program deals with regular expressions and grammars. So I gave you a very brief, quick introduction to regular expressions and context-free grammars. And this time what I'm going to do is I'm going to introduce you to mutation testing. Next week we'll see how to apply mutation testing to source code. So what does mutation testing involve? The term mutation in biology or generically means you make a change. So in biology, you make changes, cells undergo mutation, they undergo changes. When we apply mutation testing in the context of software testing, we say a software artifact undergoes the change. So the software artifact that could be mutated or changed could be a program, could be an input, could be a design document, it could be one of the several different things. So mutation testing means you make changes. Most of the time the changes are syntactically valid. I'll explain to you what that is, to a software artifact and then test the artifact. When I say a syntactically valid change, I mean the following. So you consider the software artifact to be a piece of source code or a program. Now I make a change to see how the changed program behaves with reference to the original program. So for me to be able to test the changed program, the first thing that I must do is to be able to compile the changed program. So the changed program must be syntactically valid. It should be a compilable program. So while doing mutation testing, we mutate by making changes. How are the changes defined? The changes are defined by using mutation operators. And where do the mutation operators come from? They come from grammars of software artifacts. Grammars typically generate valid strings. Everything that they generate is syntactically valid as per the production rules of a grammar. We use derivations in grammars to generate valid strings, and sometimes we use derivations to generate invalid strings also. When do we generate invalid strings in the grammar? We generate invalid strings only when we consider mutation as being applied to the inputs of a program. When we mutate a program itself, then we expect the program to be valid because it needs to be compilable. But sometimes we want to know how a piece of program, given program, behaves on inputs that are invalid. How does it handle invalid inputs? So when we do that, we mutate to produce invalid string from the grammar corresponding to the input domain. So testing based on generating these valid strings and invalid strings for different artifacts is what is called mutation testing. Mutation testing, as I told you, can be applied to program source code, it can be applied to design integration, it can be applied to input space, and it can be applied to change the requirements themselves. So here are some terms that we will use throughout our lectures in mutation testing. So I have a particular software artifact that I am trying to mutate or make a change in. That software artifact is what is called a ground string. So a ground string is a software artifact that I want to mutate. In other words, it's a string in the grammar of the corresponding software artifact. It's a string in the underlying grammar. And how do I mutate? I mutate by making what is called a mutation operator. What is a mutation operator? A mutation operator is a production rule or a rule that specifies syntactic variants of strings that can be generated from the grammar. Every string generated by a grammar, as we saw in the last lecture, comes by applying a sequence of rules one after the other, till we get a string only of terminals. At some point during the sequence of derivations that I apply, I decide to apply another rule instead of the original rule that was used in the string, and such a rule that I apply instead of the original rule is what is called a mutation operator. So I begin with a ground string, I apply a mutation operator. After applying a mutation operator, I have changed or mutated the ground string. The changed or mutated ground string is what is called a mutant. So a mutant is the result of applying exactly one application of a mutation operator. So you might ask, why exactly one? Why not more? You can apply more as long as the changes are syntactically valid and you're confident of how the mutated program will behave. But typically in mutation testing, it is recommended that you apply mutation operators one at a time. So we'll discuss this, we'll revisit this question once again very soon in this lecture. But just to move on, before we move on, I'd like to summarize. Let's say you're testing a Java program using mutation testing. The original Java program that you begin with is called a ground string. You take that Java program, apply one mutation operator, that is one change to the underlying grammar from which the Java program comes by applying some rule instead of the other rule. The change that you make is called mutation operator or applying a mutation operator. The resulting string is another syntactically valid Java program whose behavior you want to test against the original Java program. So the changed Java program is what is called a mutant. So the ground string could be a program, as I told you, could be a Java program. It could be specified using the grammar of Java. It could also be an input format specified using a markup language. Several different things take XML format. Several different software programs take XML format corresponding to an entity as their input format. Sometimes I want to be able to test the software artifact by changing the input to a syntactically invalid input or another valid input and see how the program behaves under these invalid inputs. When I do that, I use the grammar to generate implicit invalid inputs also. So when I do that, I get invalid inputs, and in that case, ground strings result as those that arise by not applying a mutation operators. For example, as I told you, when we mutate the inputs to a program remains the same. It is still the ground string, but the mutation operator is applied on the inputs to a program. The program and the resulting mutant are the same, but the mutated input is what is changed, and in this cases it can be invalid also. So here is a simple example of how to apply mutation at a basic grammar level. Next lecture, I'll show you how to apply mutation to source code by taking concrete examples of programs. If you remember, we saw this grammar in the last lecture, and these were some valid strings that were generated by this grammar. This grammar used notations that were a combination of regular expression notations and grammar notations. And this vertical bar is to be read as two rules, this rule and then this rule. So here are some examples of strings generated by grammar. This was generated by this grammar G17 08.01.90 and B13 06.27.94. Here are two examples of valid mutants. How did I get this? How did I get the first mutant? I took this string. This string had a derivation in the grammar. At some point, this G was derived. In fact, right in the beginning, G will be the first terminal string to derive after the third or fourth step in the derivation when this production rule is applied. Instead of now this G, whenever this production rule was applied, I picked up the same derivation which gave this. At that point, instead of deriving G, I applied the fourth production rule and got B instead. So that's the only change. So at some point in the derivation of this string, I decided to take out one step in the derivation and replace it with a different production rule. In particular, whatever was giving me G, I replaced it with B. So this is a valid mutant. So here is another example. I take the same string G17 08.01.90. At some point, this number 17 was generated because this rule was applied. S goes to digit 1 to 3. It picks up randomly a digit that is between 1 and 3 length long and applies it. And here the digit that was picked up was 1 and 7, and it was of 2 digits long. Instead of picking up 1 and 7, I pick up 4 and 3. So from this, I get this valid mutant. Here are examples of two invalid mutants from the string. The first invalid mutant says you take this string G17080190, instead of G, you get 12. Why is this an invalid mutant? If you see this grammar, you'll realize that no, there is no way that this particular string can be generated. You can never generate 12, 17, 08, 01, 90. The way this grammar is structured, every word of this form will begin with a G or a B. Because it begins with a 12 and it cannot be generated by the rules of the grammar, we call it an invalid mutant. Maybe these are inputs to a program and you want to check if the program throws in an error saying this input format is invalid. Here is another example of an invalid mutant. This is the same thing, G230801, and the last 2 digits of this date-like entity is missing. Here is this is an example of invalid mutant because there is no way I can generate this string from this grammar again. Because when I reach this stage where I apply this GSN or BTN and I finished applying for S, now I have to apply for N. In one shot, I generate this whole thing. I generate digit 2 dot digit 2 dot digit 2. So this one, if you see, it doesn't have the second dot and the third 2 digits. So it can never be generated in this grammar. So that's why it's an invalid mutation. So here are some do's and don'ts as far as mutation operators are concerned. The first question that we discussed a little while ago in this lecture was, should I apply exactly one mutation operator to get a mutant, or should I apply more than one mutation operator to get a mutant? So that's the first question. So should it contain just one mutation operator, or it can contain several mutation operators? The ideal recommendation that people use in mutation testing is don't do more than one. Work with exactly one mutant, it's good enough. And after analyzing that, you work with the next mutant. Experimental and theoretical evidence indicate that it's usually very difficult to track the program behavior when more than one operator is applied, because you don't know whether the change in the mutated program is because of which operator that I apply. Even if you apply two, you don't know the change. It might be difficult for large programs to isolate and say that this change is because of the first operator, this behavior change is because of the second operator. It's very difficult to do that. So always the wise thing to do is to apply one mutation operator at a time. The second question that you might want to ask is, should every possible application of a mutation operator to a ground string be considered? In the sense that I have a grammar of a program, let's say language. The grammar is usually fairly exhaustive. And if you try to generate mutation operators based on the grammar, you'll get lots and lots of operators, hundreds, sometimes even thousands of operators. So now for a given program, there could be several different ways of mutating it. Should I consider every possible mutation and test? That's like exhaustive testing with reference to mutation. The obvious answer is no, but sometimes for small programs, people say yes also. So yes, if you can do it carefully and in a systematic way. No, if you don't know that it's not useful. Typically, it's not useful to do exhaustive mutation testing, so the answer is a no. Now, what are the mutation operators? Mutation operators take the grammar and make one change with reference to the grammar. That's what I told you. Mutation operators have been designed for several different programming languages. We'll see one for Java in the next couple of lectures. They have been designed for formal modeling and specification languages, especially for model checkers like new SMV and SMV. They've been defined for several different grammars in Backus-Naur form. I keep using this term BNF. I didn't really introduce you to the term BNF. We just saw context-free grammars, but they're almost always given in Backus-Naur form. The fact that it comes in this normal form may not be very important for our lectures. So I skipped introducing the BNF part of the context-free grammars when we did context-free grammars. We don't really need, but it's important to know that they don't come in any format. They always come in BNF format. Mutation operators are also available for data definition languages like XML. They are available for several different query languages, SQL, and so on. Mutation operators for programming languages. Which are the phases they can be applied in? They can be applied while doing unit testing and while doing integration testing. There are integration level mutation operators that are also available. So what we will see from the next lecture onwards is we'll see some mutation operators for Java for a good number of lectures. And when I end mutation testing, towards the end, we will see mutation operators for XML also. Some more definitions related to mutation testing before we move on. For a given artifact like source code or requirements or design, let M be the set of total number of mutants. Each mutant M in M will lead to a different test requirement. Testing goal in mutation testing is to be able to kill the mutants. What does it mean to kill the mutant? It means the following. You take the original program called ground string, apply one mutation operator, get a mutant or a mutated program. Now, take a test case, run the original program on that test case, take the mutated program, run the same test case on the mutated program. If these two programs, the original program and mutated program, produce outputs that are different for the same test case, then you say the test case has killed the mutant. Right? So given a mutant M for a derivation D and a test T, the test T is set to kill the mutant M if and only if the output of T on D is different from the output of T on M. I hope that's clear, right? Take a program, apply one mutation operator, get a mutated program. Pick a test case, run it on the original program, run it on the mutated program. If the two programs produce different outputs, then you say the test case has killed my mutant. This definition is very important because the core of mutation testing lies in understanding or designing test cases for killing mutants. So the derivation D could be represented by the complete list of production or simply by the direct resultant final string, which could even be the program. So here are some coverage criteria for mutation testing. The first coverage criteria that we define is what is called mutation coverage. So for each mutant that you apply to the original ground string, for each mutant M in M, test requirement or TR contains exactly one requirement: you kill that mutant. So when I make a change to a ground string and get a mutant, I should be able to write a test case to kill the mutant. So if I am able to do this for every mutant, then I have achieved what is called mutation coverage. The amount of coverage that you achieve in mutation testing is usually written as the percent of mutants killed. Like for example, suppose I have a small Java program and it happens to be the case that there are 15 different mutants that I can get from this Java program. Which means what? I can make 15 different kind of changes, one at a time, to get 15 different other Java programs. Let's say out of these, I managed to write test cases that kill 15 of these mutations. Let's say the test cases that I write, I am able to kill only, let's say, 10 of these 15 different mutations that I have done. The remaining 5 mutants of this given Java program are such that no matter what kind of test case it is, it can never kill, in the sense that the behavior of the original program will be the same as the behavior of the mutated program. If that's the case, if you've managed to kill only 10 out of 15 mutants, then the mutation score says that you have killed only 10 out of 15 mutants, which means you have roughly killed about 75% of the mutants that you created. So the amount of coverage is usually means the amount of killing of the mutants that you can do is usually written as a percent of mutants killed and is called mutation score. Suppose for all the 15 different mutants that you wrote, you managed to write test cases that kill all the 15 different mutants. That doesn't mean that you've tested in a more effective way. It's in fact a myth to believe that the more mutants that I write and kill, the more effective that I have tested the program. These two don't really correlate to each other. Another kind of coverage criteria over mutation testing are mutation operator coverage and mutation production coverage. So when a grammar is mutated to produce invalid strings, like we do for mutating inputs, the testing goal is to run the mutants to see if the behavior is correct. So in which case, mutation operator coverage, abbreviated as MOC, says for each mutation operator, TR contains exactly one requirement: to create a mutated string M that is derived using that particular operator. So suppose at some point in time, there was an operator that said you use less than or equal to, and you are able to create a mutation where instead of less than or equal to, you use greater than or equal to. So this is called one mutation operator. So I write a test case to cover this mutation operator. Similarly, I can define what is called mutation production coverage. What does that say? For each mutation operator and each production the operator is applied to, test requirement contains a requirement to create a mutated string by using that production rule. So the production rule that changed the greater than or equal to less than or equal to, use the rule, make the change and write a test case to kill that resulting mutant program. So these are the 3 mutation coverage criteria. In fact, we will see them for programs and see how they apply. The number of test requirements that I need to achieve mutation coverage criteria is somewhat difficult to quantify. It basically heavily depends on the syntax of the underlying software artifact of the program and what are the mutation operators that I have considered. Typically, as I told you, exhaustive mutation testing is never done, but operators are available as a fairly large exhaustive set to choose from, because you never know which operator will come to use, and it's a fairly routine mechanical programming task to generate mutation operators given the grammar of a software artifact. So even though an exhaustive set of mutation operators are available, mutation testing is never exhaustively done by applying every possible operator that's available. People usually don't do that. Typically, mutation testing is supposed to subsume a lot of other coverage criteria. We'll see precisely a comparison to several other coverage criteria that we saw and how mutation testing subsumes which of those. Mutation testing is very difficult to apply by hand because it involves grammars, and there are mutation testing tools available. Towards the end, I'll point you to links of these kind of tools. In fact, mutation testing is very difficult. It's difficult to apply by hand, it's difficult to automate also. Mutation operators are difficult to automate, but the per se testing process, after you've created the mutated program, designing a test case to kill the mutant, their automation is difficult and you need human intervention and domain knowledge. And which operator to apply? There also you need human intervention and domain knowledge. So in the next lecture, what are we going to see? We learn how to define mutation operators, how to apply mutation testing to programs or source code to begin with. Then we'll apply mutation testing to do design integration. Finally, we'll apply mutation testing to a markup language like XML and understand how mutation testing applies to input space to create invalid inputs and how the programs react to invalid inputs. So that's the plan for mutation testing. Thank you.